the analog input. Okay, we forgot to record. I'll just continue from where we were. We just, just for the recording, we're talking about what is an ICS, right? It's a system interface with the real world, but it's a hardened system. It's not just a computer, it's more than that. So back to what we're discussing, PLCs is an example of control that we can see. One of the possible topologies we can see in industrial control system. PLCs is a more of an isolated control. It receives inputs, produce actuation, but it's kind of self-controlling, controlling like a small part of a process. If we need distributed control, many pieces of equipment talking to each other, we're looking more into a DCS, a distributed control system. SCADA refers to mostly monitoring geographically dispersed assets. That's a prime example is the power grid, that we have substations that are kilometers away, and then we just get information from all these dispersed assets, and we try to understand the state of the system. And once we get the state of the system, we're trying to control by invoking some commands. So ICS, those things, right? I mean, those images should be familiar. You may have seen them one way or not, right? Like big, like clusters of things that have lights on. The lights are needed because you want to have a good way of getting data out, right? Your visualization is important because you have to be making decisions quickly. If you're an operator, I don't know if you have seen the Chernobyl Netflix documentary, right? I mean, those people needed to see readings from different parts of the plant, of the process, so they can quickly respond if something goes wrong. This part I mentioned, like Chernobyl, a nuclear plant, power grid, these systems are part of critical infrastructure. Critical infrastructure is an umbrella term that refers to any system that can have a really nasty effect in a nation. Like if the power goes down in a country, that you can imagine how bad the situation can be. Intelligent transportation, another example, water, like water treatment and desalination, especially where I'm currently located in the Middle East. Most of the water comes from desalination processes. So attacks on desalination plants can cause a huge problem in the water supply of the countries in the Middle East. And as you can understand, the ability of those systems to work properly without problems is paramount for safety, right? And it doesn't have to be this kind of effect that something is destroyed, you have a nuclear blast, and then the whole city is devastated, right? Problems can be just the power going off for an hour, that can have huge problem, create huge problem in a country. Water being unsafe to drink for a few hours or a few days. We've seen cases in other countries, not through cyber attacks. In Flint, Michigan, they had water supply issues, not because of attacks, but because of improper treatment. And that caused the citizens of the town to have long-term effects from, maybe getting cancer or to other effects that they experienced until they realized that water supply is bad. And ICS control systems, we always been working with the idea that, the process engineers and the people who designed them, they did an amazing job in ensuring safety, right? But they had, in a way, they had one attacker in mind, and that was nature. They were not thinking about malicious actions on behalf of humans, but they were thinking, what can go wrong in my process in terms of physical effects or physical phenomena, earthquakes, or like the power going off in a plant. That can cause really unsafe conditions. So ICS, people in security who work in ICS, like myself, are lucky because we're kind of piggybacking on what the safety engineers have been doing, right? There's a lot of process that ensures safety in control systems. And the process engineers did an amazing job, and that's why things work, right? I mean, the power grid, sometimes the substation may go offline. You may have a hurricane, you may have a tree falling on a power line. Enough redundancy is built, especially within a city, to ensure that the power won't go off throughout the city, right? There's contingency, there's redundancy, there's liability built in already. But now the new thing is that we're trying to protect against people who are, are not, they cannot be modeled as nature can be modeled, right? But people who are looking to find that unique case that will cause a cascading effect, will cause a big problem to rise. So why are we having this talk today? Well, we're having this because these systems have been evolving over the years. You may have heard the term Industry 4.0 or Industrial IoT, and this captures this evolution that in the past, all these control systems were purely electromechanical, right? They were just having a mechanical control that would cause some kind of electrical, some kind of actuation that will be just some voltage coming out to cause like a breaker to trip, for example, right? But nowadays, we kind of moved out of this and we're slowly going, instead of that, what I was describing just now, we're moving to something like this, right? That the sensing and actuating are part now of a system that is CPU based. So I still get my values from the sensors, but then I digitize them and I can do way more things, right? Think of, electromechanical relay, it has limited things it can automatically do. I can pretty much do one or two things. But if I add smart control, a CPU that can read sensor, then I can have more complicated conditions. I can do if statements, I can do, let's say, calculation of integrals, derivatives, in order for me to understand whether this is a real fault, because I can measure over time, I can do calculations over time, and that allows me to have better control of my process. And besides the computing part, also these modern systems give me advanced remote debugging capabilities and monitoring capabilities, right? Now I can connect to them through the internet, for example. I can connect to them through protocols, industrial protocols like Modbus, DNP3, and others that allow me to monitor them in real time. So I don't need physical presence in somewhere that's geographically located very far. So all these things are great for improving our processes, improving our system, making them more robust, more efficient, and more optimized. And we typically do that nowadays by taking computers that, like an ARM processor, for example, and taking an existing operating system like Linux and adding a real-time patch to it, and having a PLC, right? And we'll see many of the modern PLCs use commercial off-the-shelf components at the hardware and the software too. Why? Well, why would the company create their own processor, right? Why would the company create their own operating systems? There's already an ecosystem that's very mature, both in hardware and software. So I just reuse it, right? And of course, I need to adapt it to the needs of my system. But what we saw in the past, like for example, Siemens having their own controllers, that has ceased to exist. We see more and more transition to just grab an ARM, put it in a system on chip, grab a network controller, so I can connect to it, get some memory, and then just dump Linux on it with real-time OS, the real-time preempt patch, and then that's it. You have a device that's extremely capable. It has real-time capabilities, and the hardening part. This is what you need to figure out. Like, how do you harden this further to ensure that this can work in the context you'd like it to work? And if you look at these companies, they're selling, for example, an industrial computer, and it's exactly like the computer you have in front of you, but it just has hardened electronics, right? And that's why it costs 10 times more than the regular computer. So all these things have been saying, right? IT, like a regular computer, regular CPU, regular operating systems. You can I'm trying to go to the side that now everything I know of cybersecurity problems in the IT world, in the information technology world, can be ported easily to the operation technology world, to ICS. So if I have a processor that's susceptible to an attack, I can do the same attack now on critical infrastructure. If I know my Linux distribution has a specific buffer overflow, then unless patched, this buffer overflow can be used to exploit and take over an industrial control system and then cause damage to critical infrastructure. And as we do more and more of this, then we really have to be very, very vigilant about what's happening with the security of those systems, right? And again, I'm not advocating for not doing it, right? We need to have those smart systems. We need to improve the efficiency of our processes. The only thing I'm trying to say is to be mindful of this convergence, the IT to the T convergence, and the fact that this convergence is allowing attackers to really go through the networks coming from the IT world and going down the levels to the monitoring side, control side, process side of critical infrastructure. And if these computers are Windows-based, any Windows vulnerability can be used to take over a system. If they're Linux-based, Linux vulnerabilities can be used, right? So now the reason we're having this talk today is because the systems that are existing in Power Grid look like regular computers, and attacks that can exist in regular computers can be easily ported to critical infrastructure such as the Power Grid. Are there any questions or comments? I'd like to hear from you if there's anything you'd like me to elaborate further. You can type on chat or raise your hand. Be very happy to hear from you if something is not clear. It's hard with the turned off videos to know what's, I don't have the visual feedback coming to me. All right. Something I already mentioned, ICS have been developed for robustness and functionality, right? What the process engineer did in the past, they did try a lot to make sure that these systems work, they work robustly, they work properly despite potential problems or potential disconnections or any natural effect that's expected in that locations such as again tornadoes, hurricanes, earthquakes, or rain or other things. So because of that, because ICS have to be very robust, and before we install them, we do a thorough test and many times a very exhaustive test on these devices. They are there to stay for a long time, right? Unlike our computers that we change them after a few years, or other electronics that we replace every couple of years, our phones, monitors, keyboards. Those devices are there to stay. And a typical shelf life for these devices is typically more than 20 years, and we see sometimes 40 years. So anything between 20 to 40 years is what we expect for these systems to endure. And that means that unless we regularly patch, then those systems will have severely outdated firmware operating system or software. And you now understand we're starting having issues here because in order to patch, you have to take something offline. When you take something offline, this cannot happen like our computer, right? We're very, maybe not anymore. I mean, not maybe now, but we now get a message from Windows, you have to restart your computer. And we're annoyed, say, oh, again, not again, right? And many of you may be clicking later. And your phone asks you to restart for the latest security patch, and you will probably ignore it, right? I'm not sure how many of you are actually restarting when you get that message from the computer, or you keep postponing till you're forced to restart. But think about the plant, like a power plant. They can't just say, okay, let's not produce power for a day because I need to restart my PLC. That's not an option, right? Outages exist, but they have to be planned. And depending on the infrastructure, this planning has to be done months in advance. So I can't just say, oh, there's another CV today. Let me just quickly patch my systems, and then next day, it's fine. I restart my PLCs and it's all good, right? You have to say, okay, I need to do something. If you're doing a good job as the security people of your organization, you have to have other controls in place. You cannot patch systems immediately. You have to have other ways to ensure that that vulnerability won't be exploited. And then you can go at some point in the next plant outage, patch your systems. Or you may choose to never patch, actually. That's another acceptable option, as long as you ensure that the existing vulnerabilities that you know about your systems are not being actively exploited by adversaries. So now the problem is a bit more difficult because we're trying to do security assessment of things that have typically outdated firmware. They have outdated operating systems, very old versions. Especially for the Waco device that we look a lot in my lab, we see Linux kernel version 2 showing up a lot in, when you look in Shodan, for example, you see not even like 3 or 4, there's the version 2 showing up in the results. There's version 3 and version 4, but most of the things we see are outdated versions of Linux. And this is not a secret, right? It's common knowledge that the industrial control systems have operating systems, software, and firmware that's outdated, and there are known vulnerabilities that exist. Another issue is that those computers, those PLCs that I discussed, or SCADA monitoring devices or DCS systems, they typically have limited processing power. If you take a modern PLC and dissect it, you'll see that the frequency of the processor won't be more than 1 gigahertz. What we typically see is around 600 megahertz. Its memory won't be more than 128 to 56. And its storage capacity will also be on the limited side, right? This happens for various reasons. Typically, these processors are a bit older and built in older processes, like 120, 180 nanometers, that are known to be less susceptible to environmental conditions, and they're way more mature. So we choose older CPUs that are, well accepted, that are robust, and they're fine. The functionality is not affected, for example, electromagnetic radiation nearby. So the fact that we have limited processing power in those systems is making modern security solutions problematic, right? Now, many of you may be submitting papers to conferences. You say, let's put a DNN, right, and do machine learning, or a CNN and do machine learning, right? This is heavily, the computational power you need to do these things is actually pretty intense. You cannot just dump a machine learning model on a PLC and say, whatever, it can do it, right? Well, it can't, not just because it cannot run it, and also because it may interfere with its real-time requirements. Remember, the main job of the PLC is to have appropriate real-time assurances and guarantees. So if my PLC has to be monitored something every nanoseconds too fast, every millisecond, then I cannot have my Norton antivirus on it interfering with that, right? So anything that is computationally intensive cannot be really used in a PLC. I need to think of solutions that are lightweight and are suitable for something that has very limited processing power, both in terms of CPU and RAM, and at the same time, it does not interfere with the actual function of the PLC, and that is the scan cycle, the read from an input, compute, and actuate. So, am I selling you snake oil here? Right? The answer is no. We've been seeing attacks on ICS, and I'd like to pause for a second, and I'd like to ask if you can name any attacks that you have seen on industrial control systems. There are a few famous ones and then a few more scary ones. Use the chat, or again, feel free to unmute and discuss what you know already about real-world cyber attacks. Stuxnet, right? That's typically the first answer we hear. Anything else? The Ukrainian power grid, yes. Water distribution in Israel, I'm not familiar with that. I know there was kind of a SCADA, nothing like VNC login in Florida somewhere, but the Israel one, I haven't seen that. USA gas pipeline, I think you referred to what happened recently with Colonial Pipeline. And that was, even though that was an IT attack, that was a ransomware attack to the IT systems, it's still the fact that the IT systems were offline that affected the OT part too, the operation technology part, and that stopped the functionality that had problems with the business continuity of the operations. So even though the attack was targeting the IT part, it can be measured as an ICS attack. Mohsin, this is Stuxnet, right? The Iran power nuclear plant. That's Stuxnet, this name for it. Thank you, Solon, for sharing the link. I'll take a look during the break. Honda factories, that's also something I haven't heard myself. Tuan, if you have a link, please feel free to share. The highly publicized ones, again, are Stuxnet and the attack on the Ukrainian power grid. Actually, that happened twice. These are the bigger things we have seen for industrial control system attacks. I mentioned a few here, but there's a lot more. And what I wanted to make sure that you understand is there are probably many, many more, right? These are not attacks that easily see the light. They're not publicized. Stuxnet was publicized way after it happened, and it was probably publicized as an intimidation mechanism, right? As a superpower way of saying, this is what we can do, so don't mess up with us. Ukraine power grid was, you can understand, allegedly it happened, from Russia to Ukraine, and for people who even remotely following the news, you can understand why this can happen, because the tension that exists between Ukraine and Russia currently, or that existed in 2015 and 16 when those attacks took place. I have Triton here on the slide too. Triton is what happened in Saudi Arabia. There was an attack that targeted the Schneider safety systems, and it was really well. It didn't lead to any problems, but the fact that someone was in control of the safety systems of a petrochemical plant had the potential to create massive damage. It didn't. But we don't know whether it didn't because someone tried, it didn't succeed, or people were just waiting for the right time to actually deliver the attack. So these three things are the big things we've seen. There are many more smaller things, but these are the ones that are nation state to nation state attacks. Sometimes we have individuals trying, like a water attack in Australia somewhere, or the VNC takeover in Florida, somewhere else. These are simpler things that just like small oversights, but these attacks I mentioned here are big, and they're like show the potential of industrial control system attacks. All right, so this is more of, I tried to give you more information on my introduction, right? Feel free to ask any question about what and how and what's happening. But up to this slide, what I want you to have is that let me not enumerate. I may not catch the number. Modern ICS appear in critical infrastructure. ICS are now switching to computers that look more like computers, so we can do attacks like we do on computers. And third, we see attacks already, and there are many more attacks that we haven't seen. So we need to do something, right? We need to revisit security for ICS because it didn't exist. Those systems are there for 20, 40 years, and they were never designed with security in mind. So we need to repurpose, we need to retroactively fit security solutions to the systems. And we have a lot of constraints when we do that. The systems don't have much power. They have real-time requirements. We have to be careful because we can't just, you read papers and they have these machine learning methods and they say, yeah, it works 99% of the time, accuracy. Well, that 1% can be bad, right? I mean, if you fail to detect, that's pretty bad. Also, if you have a lot of false negatives, right? If you say, oh, this is attack and it's not, if you are on the Codesys side, right? That's terrible too, because if you turn off the factory every second or every minute, that's not a good solution either, right? So anytime you want to discuss machine learning anything for ICS, you have to look at everything, both the accuracy, but you have to look also what's happening with your true positives, true negatives, and false positives, right? Anything matters in industrial control systems. So now, as we revisit that part, how do we go and do security for ICS? We have to think about all these things, right? Don't think about, I'll do machine learning, right? No, don't do machine learning. Probably maybe one of the worst things you can do today. Machine learning can be great for some things. It's probably really bad for many things that we see here. We can't afford to say whatever, right? False negatives. No, this is not an option, really. So now we're trying. It's kind of security is it's really bad to be on the defender side because you don't know what's coming to you. Security is a moving target. Nothing will be 100% secure. Security is a risk management approach, and we're trying to understand our threats, quantify risk, introduce likelihood, and then we'll have a risk management approach, and we'll say, I'll try to protect against my top 10 threats. But that's what I can do, right? And many more things that can affect my system, but I'll choose the top ones, the ones that are the more likely to happen and that can cause the most impact. You introduce your own equation about these things, and then at the end, you always need to assume that an attack will happen and have a proper incident response in place. But now where we stand for this talk is how can we understand security for ICS, right? How can we find how to defend our PLCs, our main core of computation in industrial control system? And I have a few ideas here. I'll mix them. So some part here will be our research, but some part will be also like giving you an idea about the landscape, right? Like what is the landscape that exists out there and what we're trying to do, but also you can understand like what generally can be done, and you may get ideas to do your own research on this topic. So what I'll present for the next few minutes is that a PLC is in continuous operation, right? Remember how I try to motivate the problem. A PLC is always on, it never goes off, and it shouldn't go off. And it's there and cannot take it off for testing or for security evaluation, right? So in a way, I'm trying to assess the security of something that I should not touch. I should not change, I should not affect. So how can I do that, right? How can I know the vulnerabilities of something I cannot really take offline, dissect, and look at the internals? So the solution to that, the solution that we are promoting, right? But again, you have to think that there could be other solutions too, is emulation, right? Instead of doing security assessment on the PLC directly, create an emulated instance of that PLC that is accurate, and then do a security assessment on that PLC, on that emulated instance. And this emulated instance, one way of modern security assessment is through fuzzing, right? So you can fuzz and crash the emulated instance. So, you're not affecting the real PLC, but you're experimenting with the emulated instance. Let me again ask a question to gauge the audience. Do you know how to do system emulation, like how to emulate a device? Is that something that you're familiar with? A couple of yeses. No, a couple of no's. All right, not on the no side again. This is a way for me to get a break and also to get a sense of what I should emphasize more in this first part. So Maria is right. Emulation really depends on what you're after, and a PLC simulation may be a bit more tricky compared to a regular computer emulation, because PLC emulation relies a lot on external inputs from the real world. And unless you emulate those two, then you can't really have a proper emulated instance. Second question, right? How about fuzzing? Who here knows what fuzzing is and can utilize a fuzzer to do security assessment? Yes, on fuzzing. Fuzzing probably I expect to see more yeses on the fuzzing side. Right? No's again. Okay, that makes my life easier. So I can talk more about things since some of you are not familiar with the terms. So what I'll explain, and I will finish the first part. Let me find the clock. The first part with is again this non-intrusive security assessment of PLCs. And non-intrusive means create an emulated instance of the PLC and try to find problems there. And the way we find problems there is through fuzzing, but there are other ways, right? You can do symbolic execution analysis, you can do things like that, or static analysis and other things. We do fuzzing because that's typically how you start. So in this talk, I'll talk about Codesys a lot. Codesys is a very good example of this modernization of PLCs because it's a framework that can be applied on any computer, right? You can even put this Codesys framework on BeagleBone and have a PLC-like computer, because Codesys sits as firmware, middleware in a way, on top of a Linux computer like a BeagleBone, and gives you this interface between the real world, like sensors and actuators, and also give you the ability to program PLC languages like ladder logic or structured text or function block diagram or whatever you'd like. So Codesys is a very good example for this analysis. So the Codesys runtime is, as I mentioned just now, the evolution of PLCs, and this is employing the Linux operating system with a real-time patch on any processor, right? We'll use ARM for now, but you can pretty much use it on anything that runs Linux, and that's also anything. Currently, we're at 25% market share, and that keeps increasing for Codesys. The big players like Siemens, Bradley, Honeywell, Rockwell, they would have their own ecosystem that they try to keep maintaining themselves. But we see other, like the smaller players, but we even see the big players slowly transitioning to that. The fact, again, I take a framework that can be applied to any computer and just build my stuff on top of that. Why is that a great thing? Well, think about, you have a computer, you have a PLC, and one of the features you'd like to sell to your client is that you can remotely connect to the PLC, right? And in the past, that was sold as a huge feature that you can maybe connect the PLC to the internet. So you don't even need to create your own dedicated connection. If think about the substation that's 200 kilometers away, right? How do you connect to it? You can run a very long cable. That's probably a bad idea. You can try to have radio communication through microwave frequencies. So depending on the distance, this can be good or bad, but then you susceptible to jamming. Or you need line of sight, and the clouds and rain, you may have communication problems. Or you can connect to the internet, right? That's robust. But then you connect to the internet, and whatever that means for the security of your PLC. But in the 90s, connection to the internet was sold as a huge feature. And to connect to the internet, you need to create, as a vendor, when you sell the PLC, you need to create the code for it, right? You need to create your web browser, you need your HTTP client, you need your FTP server, you need your TCP/IP stack created. So you can rewrite all these things, or you can just use Linux, right? Linux has all these things built in. And nowadays that we're looking into more security, you can use Linux OpenSSL libraries for your security needs, for your VPN needs, for your FTP server connections. So you don't need to recreate the cryptographic libraries for SSH connections. You use what Linux has already. So having the Linux OS gives you all these amazing libraries that we all use in our computers already there, and they're mature, right? You can trust nowadays, right? In the past, if you remember the Debian fiascos, I mean, we've seen like horror stories with Linux too, but you know, nowadays you can trust the cryptographic libraries that exist in a Linux operating system. So instead of one programmer in a vendor writing really bad cryptography code, and you know, one thing you learn when you do applied crypto is never employ your own crypto, right? And even if you do standard crypto like AES or RSA, you can mess up the implementation. So just take it. Don't try to create it yourself. So Linux gives you that, right? So as a vendor like Wago, as a hardware PLC provider, I don't need to create my own crypto libraries. I just use Codesys and Linux, right? And that's about it. I'm done. I can sell that PLC to someone. However, this now creates a very interesting ecosystem that exists on the modern PLC, right? And this is a slide I'd like you to really focus on, and that's, you know, if you are to remember one thing from this lecture, this should be, right? That slide should be the one. So, you know, we talked about proprietary hardware, right? But, you know, nowadays hardware, again, is commercial open source. So you have, in a way, in a modern PLC, you have a mix of proprietary things and open source. So some things are open source, some things are proprietary, right? So let's run the stack from the bottom to the top. So you have your hardware that, you know, it can be an ARM processor. And on top of that, you put Linux, right? Linux is fully open source. So you take your Linux system, it's written in C, whatever that means for Linux, right? Well, vulnerabilities exist if you write in C, but Linux kernels are extremely mature nowadays. Vulnerabilities, of course, arise from time to time, not so much for the kernel, but really with what's happening with the packages on top of the Linux operating system. So you have real-time Linux, and then on top of that, the vendor like Wago or Siemens, Ale Bradley, they have their own PLC runtime that, in a way, is an operating system on top of the operating system, like a virtual machine, right? That PLC runtime is created by the vendor. It's like software, like a virtual machine that runs on Linux, but it hogs all the resources. It runs as a root that creates its own problems, actually. So the PLC runtime, it is now proprietary code, right? So we have open source Linux and we have Wago Codesys runtime that the code is closed source. So we have pieces of code that they have the property of being mature because many eyes are looking at them. So you have vulnerabilities that come more often, but they're fixed more often too. And then we have the proprietary side that we don't know whether vulnerabilities exist. If someone finds them though, they won't publicize them. They can use them for life, right? Because company, they may not find the vulnerabilities. Linux, we see them all the time. We fix them all the time. Proprietary has a different pace. They're more infrequent, but we also don't fix them as frequently. So we're talking about the same system with very different paces of vulnerabilities showing up. And also the rate of fixing is also very different. That runtime is written also in C or C++, and whatever that means for vulnerabilities. And then that runtime, what it does actually, it runs everything a PLC needs to work on. And its main thing is the PLC binary, right? What is the PLC binary? It's a main control. When we talk about industrial control systems, there's a control inside. What the control does, well, it can be a PID, for example, like A controller, like you see that a proportional derivative integral controller that reads a number and calculates the integral of the number and uses that to produce actuation, right? That is typically written in a different language than C or C++, because it's being written by an expert who's a process engineer, not an IT programmer. So there exist dedicated languages that process engineers can use to write that code. You could write a PID controller in C, but the person who needs to write that is not a C programmer, right? They can, they can think algorithmically, but they cannot use C, or Python didn't exist back then. So those languages, for example, I have here ladder logic, function block diagrams, or structured text. They are custom, they are IEC languages, and they have a custom compiler. It's not GCC anymore, right? You see, I have GCC in all the other parts, but here I don't have GCC. This is a custom compiler. So that means I have vulnerabilities from the compiler itself, from the languages that are different from the vulnerabilities that GCC introduces and the other languages are using. So you may get in a better sense of why this is a big problem. Open source, proprietary, different compilers, different programs, different attitude of programming, like Linux, open source, proprietary, and they're all together exist in a system that has to be defending against vulnerabilities, right? So it's not an easy problem, right? The more we work on it, the more we realize this is bad, because you follow a different approach to, with proprietary code, you have to follow black box approaches because you don't have the source. So you have to do different things to find problems. In Linux, it's a bit easier, but a bit harder at the same time because it's a very different surface. It's much bigger, and vulnerabilities are being, you find them much more frequently because many people have the same Linux operating system. And on top of that, remember that these systems are not updated frequently. So if vulnerability appears in the Linux kernel, it will exist in the PLC for months or maybe years. So going up the stack, Linux runtime, and then the runtime has threads, and every thread does a different thing. For example, Modbus communication, that will be a thread on part of the runtime process. SSH connection, that's another thread, but the SSH thread is open source code coming from the Linux operating system, while the Modbus, it is custom code coming from the vendor. They still coexist as threads as part of the runtime process memory space. And again, besides that, different compilers exist. GCC with its own problems, custom compiler with its own unique problems. All right, is that clear? Again, what I'd like you to keep here is that the modern PLC is a mix of open source and proprietary, and it's difficult to create a holistic approach towards security assessment of such devices. Any questions? All right. Okay, there's a question. Leonidas is asking whether PLC runtime supports binary protection mechanisms such as no execute, canary, NA, SLR. That's an excellent question. So we see that the vendors are slowly picking up something from here, but those actually, the answer is no. But the no execute thing is what we start seeing recently, only that, not canaries or ASLR. So Codesys 2, version 2, did not have no execute protection. Codesys 3 has no execute protection. So in a way, they evolved to add some security mechanisms, right? Still, canary and ASLR don't exist. KASLR is not enabled in the kernel because, probably when they do the threat modeling, they realize that the attacks such as, heap attacks, stack attacks, heap spraying, stack smashing or the attacks that can bypass no execute bit or op return-oriented programming are not really threats and attacks they expect to see. So, but I'm not in the runtime development, so I can tell you that's my thinking. But yeah, again, the short answer is the latest version supports only no execute, the NX thing, but the others are not there. All right, moving on. So I did mention that the runtime is the process of the operating system, right? So if we see here, this is connected directly to the PLC. I see the runtime is being loaded near the end of the booting process of Linux, right? So you see all these things happening before, networking, cron, the communication bus for the I/O, and the keyboard, the serial, all these things, right? I think all these things, the vendor doesn't need to program them, right? They take them from Linux directly. The only thing they add is their own runtime. So the runtime is just another process, right? It's a special process in a way, though, because it does run with root privileges, and that's needed because that process is the one that interfaces with the sensors that they have to go through the I/O, right? The input-output system. And then, if you look at the processes running, that falls directly on my Zoom. Okay, so if you look at the processes here, right? So you see the Codesys process. We see that 730, and that process has a lot of threads, right? And you see those threads. This is what I was trying to say before. You have the process and you have the threads. What are these threads? Well, it's what we expect them to be. Modbus communication, right? Scheduling, the real-time scheduling of the PLC, like the scheduling processor and the event. Synchronous communication. This is what I call the scan cycle, like the fact that we have this runtime that loops and does input, compute, actuate. So this is Wago gives you advanced visualization through a dedicated web server, so you can actually use HTTP to connect to the PLC and get information coming out of it, right? So this is a very advanced feature of the PLC. It gives you that capability, and that's an amazing capability to have because it really helps the process engineers have visibility to the process. So after going up the stack, up the thread process in a thread, and here that gives you information about the memory or the memory layout of the Codesys process. And I'd like to ask, what do you see here that's pretty bad in terms of security properties of the process? Exactly, Leonida. Heap and stack are executable and writable, right? That's terrible. Terrible in terms of security. Why? Because you can send your code, your payload, and you can execute things from the stack. You can execute your own payload if stack is writable. Let me ask a more difficult question. Why do you think the Codesys developers made the decision to have writable and executable stack? I'm pretty sure the answer is not because they wanted security to be bad. It's a functionality question. It's a functionality answer. Now, Solon, you have to think closer to how things work in the internals of the operating system, right? Remote control, if you're talking about like accessing PLC remotely, that's a thread, right, that runs on the process. It's unrelated to the question here. The answer, it's not obvious. Don't kill yourself if you don't think of it. So the answer is that remember, go back, focus on time. The answer is this here, this part here, right? The PLC code is creates code that exists as a PLC binary. So this is assembly, this is machine code, right? But this code has to be loaded by the runtime. So to load assembly in directly, we load it in the stack of the PLC process, of the runtime process. So the code of the PLC is being loaded after, because you can load any code. You may change the code you have loaded, right? That control code I discussed. So that code is assembly. And for this to be executed, since it's assembly, and since it's been loading to the stack, because it's being loaded afterwards, the stack has to be executable and writable. The writable part is not the problem, right? In stack has to be writable. The executable part is the problem. So because I need to execute the PLC binary code coming from a custom compiler, the developers of Codesys decided to make the whole stack executable, which is, for people who know basics about security, is a terrible security practice. And now we can, if we can write to the stack, because we send data and that data goes to the stack. So if we can execute our stuff, then we can send the malicious payload and that can be executed with proper control flow redirection. So here, I point out that the stack is executable, right? The X here shows that the stack of the Codesys runtime is executable, and that's really bad. So also because this is recorded, I'm not trying to say here that the runtime is bad, right? What I'm trying to say here is that the runtime has been created for functionality. Decisions have been made in the past to ensure that it works properly and robustly, and it does. And we've seen real PLCs using the runtime, right? But we see more and more CVs showing up, because when the runtime was created, security was not a big concern. But now that it is, we've seen more and more CVs coming out for the runtime itself, that more and more researchers are looking into these things and finding problems with the runtime, and the fact that, it's not only what I discussed, right? Many of the problems come from like the external libraries that the runtime includes into the process. Some examples of CVs: uncontrolled memory allocation, privilege escalation visualization module. That module is the last thread you saw, the web server thing that the runtime offers. Again, uncontrolled memory allocation in another part of the process, exploitable code execution in PLC program loading, remote code execution through heap overflows, right? So this is only the things we know. And my personal opinion is that there are many more things we don't know yet, because the runtime is not open source. So all these vulnerabilities were discovered by researchers trying to do black box testing to the code, right? And this is way more difficult to find security vulnerabilities if you cannot see the source code of the runtime. So I think that there are many more waiting to be found. And that's why exactly that was the motivation for us to create that line of research, that we try to automate security assessment for this computational stack, for the PLC binary and the runtime, because the binary and the runtime are different things, and they have to be, the security has to be assessed differently. All right. Any questions up to here, up to the runtime and the computational stack? No? All right, so 15 minutes till the break. Let me explain a bit more about the PLC control application, or the PLC binary, right? I've been using these terms interchangeably. So the PLC control application, think of, it's the heart of the PLC. It's the control, like it's the one thing it should be doing, right? All the other things, FTP connection, SSH connection, HTTP server, are extras that have been added for remote diagnosis, remote connections, and all this. So the controller, what it does, as we said, it receives an input, it computes on it and creates some actuation, right? So a controller can be, again, a PID controller, it can be a single saturation controller, and again, I'm not a control expert, right? I'm learning these things as I look into more and more processes. But it is a piece of code that reads an input, computes with some instructions, and produces an actuation. So this control logic, it is, physics in a way that you have to code into an application. And then the Codesys platform gives you a framework that you can code in the dedicated languages for PLCs. So you use that IDE, you code that controller, you compile it, and then you can load it with a runtime on the PLC. But this compiler is custom compiled, right? It's not GCC that we're used to. GCC takes C or C++ and outputs assembly. This here takes ladder logic and creates assembly again. And this assembly is being loaded by and executed by the runtime on the PLC. The option of languages you have is quite a few, and the ones we discuss here, the ones standardized by EC with 61131 standard they have. So there's ladder logic, and I think in the next slide I do have examples of this. Ladder logic is the simplest that you can use, and yes, it looks like this. In a way, it looks like a ladder. That's where the name comes from. They're like rails running on the sides, and then you just connect things on the step, right? So in a way, the rails are running from one to the other, and you just put things on the step of the ladder. So here, for example, based on enable switch, you have, what does this do? It just adds one to the input, right? So it takes the input, adds one, produces an output. That's control, right? That's, I just add one to my input and I output it, right? That's an example of a control. So you don't write C. So this is the corresponding code in structured text. I have it as an example, because that's easier for IT programmers to understand. But this is what you would call, you just drag and drop boxes and create your control logic. There's the example, another language is function block diagram, that it is also graphical like ladder logic, but it's slightly more complex because it doesn't have like a standard input and output. You have more complicated control flow, and in a way, everything is a box, is a functional block that takes input, it has inside an operation and produces an output. So you just connect, plug in those boxes back and forth, and then you produce an output, a down signal, output, and whatever you want to do, right? It looks like ladder logic because it's graphical too, but it is more complex. It doesn't assume or need only a left to right flow. It can be way more complicated than that. And another standardized language is structured text. That is the closest we have to a regular imperative programming language like C or C++. Actually, structured text is loosely based on Pascal. If you look at the code, fun fact, Pascal is the first language I personally learned before transitioning to C. So with code like line by line sequential statement based languages, you can do now more complicated stuff. It's much more complex. It's much more expressive. In a way, it supports pretty much what you would do using a language that we're comfortable with, like Python or C. And you can see the code on the bottom of the page. If enable equals true, then that's output equals input +1, done or not done, right? So if it's not enabled, you're not done. If it's enabled, add 1 and you're done, right? That's about it. That's control. It takes an input and computes. Compute is just +1 and produce an output, an actuation. What's the actuation? Well, +1 of the input, whatever that means in the process you have. So these languages that we discussed, you can use the ID of the Codesys framework. So here I have an example that you have the program on top and the, well, what's the input output that you define, right? What are the inputs? It's an analog input coming in 0 to 10 volts. Enable is a digital input, enable or not. Done is a digital output for LED indication. And your output is another 10 volt output, right? And that's an example of code. And then you just compile. You hit compile, and this will compile, and you see errors or warnings depending on whether you have some syntax error or some other problem in your PLC. So the security assessment of this is very different than assessing a C program, right? C programs, we know what to do. Well, we think we know, right? There's a lot of research on that. But here, this is new, and that's why I have been focusing on that. And that's why we further discuss it in this class, right? A modern PLC has this as a major component, like, because that's the heart of the PLC, it's control application. All right, so as I said, the control logic has, it can be as simple as add 1, or it can be controlling something very complicated that, it has to calculate derivatives, integrals, collect data over time to be able to make a decision, right? So the control application can be very simple and or it can be extremely complex, right? It's not very clear. It really depends on the process, on the exact critical infrastructure process that it controls. In this framework, the binary is not a predefined binary format. It is more of a collection of assembly instructions. And the compilation process is not known to researchers. It's proprietary, and it takes that language and produces assembly. And if you are if you try to reverse that binary, it's extremely difficult actually to figure out what is happening with the code, because it doesn't have a header. It's not an ELF. It's not anything we know. It's just a bunch of assembly instructions put together. And unless you know how to reverse it, it's extremely difficult to reverse. And we have, let me have it here. So yeah, it looks like spaghetti code. We do, and bin walk gives you nothing, but it does look like assembly, right? It is a set of assembly instructions. So we have a tool that should have put the GitHub link here. We call ICS Ref, and that's something we published in NDSS in 2019, and it's available on GitHub if you want to use it. That takes those binaries and reverse engineers them. So you can take this custom code that looks like a spaghetti series of instructions, and ICS Ref will extract the structure for you. So it will find the headers, the symbols. It will find the actual control of interest, because there's also overhead before and after the logic function, and it can find the logic function and the input-output to it. And it started, that research had started from a grant we had from the Office of Naval Research of the United States. And they wanted us to automate like a red team in a box. Like, how can we create a program that reads control logic, creates an attack, and mounts the attack, right? So this tool was part of this project, that it can read automatically a PLC binary. It can find the control logic, it can change the control logic, and then put the patched binary back to the PLC. So the PLC now is infected, but it's a PLC malware, right? It's a PLC attack. It's process aware to an extent. So the binary that we're discussing now, we just said it's not an executable binary. It cannot be executed by itself. The binary is not independent, and it has to be loaded by the runtime, right? The Codesys runtime loads the binary. And how this happens, and I think that can be the last slide for the break. So I have the Codesys main process that creates threads, right? And actually what Codesys does, it does create a placeholder empty thread as it creates the other threads too. Modbus, KBus, DNP3, web server, visualization task, all the threads, there's one thread that's placeholder thread for the binary, because the binary is loaded actually near the end. So through a command or an open system call, I keep reading the contents of the binary and I load it my stack, right? Because I mean, I already have my set code and data. And now the thing that remains to be loaded, it's a file. And the file is being put into the thread stack, right? So now you have code in the stack. How can you execute it? You have to make the stack executable. Since the binary code exists in the new thread stack. And then two more threads are created. One is the PLC task, and the other one is a KBus cycle task that ensure that the timer that whatever you have defined to be a scan cycle, I run the thread again. So I have a code that will run in intervals in an infinite loop. And this loop duration is hard to control with interrupts. And those interrupts are being controlled by this PLC task thread. The KBus is tasked with controlling the peripherals, the input and output. And then the placeholder thread dies after the others take over. And then execution, as I just said, the PLC task is handling the logic. Again, the logic can be, infinite loop, read, sleep. Right, and then the scan cycle, and then if sensor comes in, then you can separate the sensing from the actuation, and when the sensor gives a new value, then you can actuate on it, like close valve in this case. All right, so with this slide kind of ends the technical content of what's really happening in a modern PLC in terms of operating system internals. Then we will discuss threats and other things. Before we take the actual break, what I wanted to do is to let you choose what you want me to focus on. Where is the slide? Oops. It's like you decide Greek series, like I don't know if those exist in Cyprus too, that you were able to decide the continuation of the series. So I don't know how the poll will be, shared with all of you, but I'd like you to take a look at the slide I'm trying to present, and I keep failing here. And I can spend the second half of the class discussing in detail some of these things, right? Either more on the operational stack, threat modeling, anatomy of an attack, look at Stuxnet in detail, like step by step, risk management, generally talk about network security for ICS specifically, discuss topologies for defenses, or just talk about state-of-the-art research, like some of our work that we have done in the past. So I see Andreas has posted the doodle poll. Please vote, and then in half an hour, we'll continue with the class. And if you have any questions in the meanwhile, just put them on chat, and I'll take a look when I come back. Right? Thank you.
Thank you very much, Mihalis. So the idea with the poll is that they can click on the link and they can select from options 1 to 8. And then we will see the results. So Mihalis, how long do you think we should leave the poll open? Like 5 minutes?
No, I mean, let people, I think the result in 30 minutes, right? I don't mind.
Okay.
So once, yeah, I would come back, I will see the number and I continue with that.
Okay, that's great. Okay.
Right.
So we start again at 12 Cyprus time.
Yes.
Thank you, everyone.
That's how we start?
Yes, I think you can go ahead.
All right. Thank you. Welcome back to the second half, second part of this very short class. So I see there was a tie between the computational stack and Stuxnet. But see, we already saw some part of the computational stack here, and I'll continue a bit so we can finish that. I'll do Stuxnet, the dissecting Stuxnet class module after we finish that. So we go back to the presentation. Here. Oh, we stop here. All right, so this is where we stopped discussing how the binary is loaded, and then now the question is about the potential threats on the PLC binary or the PLC control application. And remember, to implement a security attack, what you do is you give it something, right? You give some input to it. So the compiler doesn't know whether the threat is coming or not. So there's an input as a payload coming to the binary. That input can come from something, a sensor, or through the network, or through some other way. And if you look at this example here, look at the right side, I have an example of a structured text code. So you have indexing to an array, but the indexing to an array can be an input, right? So with this, you can have an out of bounds read or write to the PLC memory. And the PLC memory, as we saw, we already discussed before, it doesn't do a good job in security. So here is an example of it's buggy, but it can be malicious too, right? Of a problematic PLC control application, something that can cause a security alert by overwriting the buffer overflow, and potentially changing a return address in order for you to execute your own code. So besides the control logic itself, right? So the code you write as a PLC programmer, there's a lot of helper libraries available to you. And these libraries, you know, for timers, for doing more advanced mathematical functions like sine, cosine. So these are given to you by the framework, similar to how in C you get your ICD stream, your IO stream, and you can use it for, you don't need to create your own input and output from the environment. So these third-party libraries are like C-like libraries, and they do some low-level memory management. They do lack bounds checks. I think I have a table here. So if you look at the table for both versions of Codesys, so we have operations. So the actual name, I think the table is a bit messed up. So these are the names in Codesys, the second column, well, third if you take the titles. That says sys string copy, concat, sys map copy. So these are the functions in Codesys that loosely map to C functions we know, like string copy, string concatenation, memory copy, memory set, mem move, and memory compare. So we played around with these functions because typically these are the functions that are exploited when you do array manipulation. You try to see whether the function you're calling is checking whether the array is of the right size. And if it doesn't, you have a bounds check problem that can lead to a crash. So we found out that the only function that checks the bounds of the strings is a concatenation function. All the others don't check whether you're supplying the right size. So you can give, you can have a buffer of 40 characters and you can send 100 and it will take the 100 characters. However, not all of them lead to a crash, especially the string ones. Even though there's no bound check, strings exist in a very special location of the memory. So even if you overwrite, you don't go into the return address that exists in the stack that you can use to overwrite where you're going after. However, memory is not the case, right? So our crashes mainly came from memory. So you see here the three ticks, mem copy, mem send, and mem move actually led to a crash of the PLC when an invalid input was given. Invalid means overflowing the buffers, like the memory contents, the memory locations to be copied from and to. We told the program to send more bytes, and that overrode some address, and then that led to a crash of the PLC. So Codesys has functions that are C-like, but still those functions have some securities, right? And through fuzzing and through other mechanisms, this is how we try to understand the security of these functions. All right, so the challenges we discussed so far is, first one, there's a compiler that doesn't check for bounds when it compiles from ladder logic or whatever PLC programming language you have. It doesn't check for bounds. It just maps things directly to the binary. And on top of that, there are third-party libraries coming in and being linked to the main PLC binary that are untested, and we don't really know whether they have vulnerabilities either. So that's one problem. Second problem is that, to test these things, we need the PLC. And to test with the PLC, PLCs are not cheap to obtain. They're not fast. So if you are to do some kind of a fuzzing session directly on the PLC, crashing a PLC and restarting it can take a few minutes. So you end up doing maybe one fuzzing session per 5 minutes, right? That's a very slow speed to meaningfully assess its security. And the PLC must be engaged somehow, right? You have to be working with the PLC. So that means you cannot use a PLC that actually is operating in the field. So we need to have a spare PLC that has exactly the same configuration, and then we can do the assessment there. So to address those challenges, we use what I discussed before as fuzzing and emulation. So challenge one, the fact that there's a lot of weaknesses and untrusted libraries. We try to do assessment using fuzzing. Because we don't know the compiler is proprietary, and also the libraries are pre-compiled, so we don't see in black box and we don't see inside the source code and have to do black box analysis. And fuzzing is a prime way to do that. For the second challenge, the fact that the PLCs are hard to use, we use emulation, right? Something I mentioned before. So what is fuzzing? You mentioned that. Some of you know what is fuzzing. So someone is asking whether OpenPLC is accurate for this kind of analysis. So OpenPLC is not tested. It's not something people use in real life, right? So it puts a question into the practicality of your and the real time and the real usefulness of your methodology, right? Because what we discuss here is a bit unique to Codesys, and Codesys is used a lot, and many critical infrastructure are using those PLCs, and none of them are using OpenPLC. So I don't know exactly the computational stack of OpenPLC, but keep in mind, Codesys also has free versions, and what we do most of the times, we employ it on a BeagleBone. So there's Codesys Control that you can put it on a BeagleBone. So that's very cheap, almost free. And you can do the same analysis, right? So if you are thinking about doing it, I would encourage you to do a similar setup that's cheap. OpenPLC, it's someone's code, right? You can write that code too. It just reads and reads sensors and then actuates. So it wouldn't give you, like, for example, the fact that the stack is executable, right? I mean, that's very unique to the framework we're after. So those things are technical details, engineering details that are unique to the framework. So you may find different things for OpenPLC, but if you try to address those, they won't have any real world effect, right? You're not really helping anyone. You may understand a few things, maybe on the physics side, sensor to actuator, but actual technical details of the stack, open source, proprietary, executable stack, threads, processes, process memory, loading a binary in the stack, those things are unique to the frameworks. So fuzzing, in a way, is fuzzing is somehow lazy testing, right? So instead of you trying to find what can crash your system, you let the fuzzer do it for you. And fuzzing, what it typically starts with is corner cases or unexpected inputs, right? For example, you may have a prompt asking what is your name, and then you respond with -1. So the system will never expect a number as a name, right? So because of that, it may lead to a crash. So that's typically how fuzzing is motivated, that you provide corner cases, weird inputs, and then you see what happens to the system. But then as you see crashes and as you see lack of crashes, then you have to choose your next fuzzing input. And that choice can be dependent on how you want to explore the input space. So in a way, you take an existing input and you mutate, right? You slightly change it if you see some abnormal behavior, because you expect a similar input to be causing the same kind of behavior, right? But I mean, you can look up the fuzzing literature. The only thing you need to know here is that you need to feed the binary with inputs, right? And there are two questions coming here, right? How do we feed inputs, and what kind of inputs do we feed to the binary? And this is both things are a problem for PLC binaries, right? Because feeding the PLC, we don't have a terminal. It gets its input from the sensors, and also how to get visibility over it, we can, because we don't have control over the execution, right? So execution control is a problem, input control is a problem in fuzzing PLC binaries. So this is an example of mutation that you can, see something you change, from 0 to 1 or 1 to 0, and then you have another input, and so on and so forth. To get visibility to fuzzing, typically you would go to binary instrumentation. So you would add things to the binary in order for you to see the effects of fuzzing. So you see an example here. I have assembly in the slides. So let me skip those. On the emulation side, so we talked about fuzzing. Emulation side, emulation, as I mentioned in the first part, you're trying to abstract hardware into software, right? And TIMU, for example, is an emulator that we use a lot. So you don't need to have the PLC to run code for the PLC. You can create an emulated instance that will have the basic functionality you need, and then you can run code on that emulated instance. So this, in a way, eliminates the dependency to the physical device. You don't need the actual PLC to do analysis on the PLC binary in the system level setting. And when you do emulation, you can do emulation directly of the binary. So you just execute it assuming a device exists, or you can do system emulation so that the PLC exists and then the binary is loaded there. That's a much more heavier emulation, though, as you understand, since you're also executing the operating system. The emulation gives us another benefit, right? Besides the non-intrusiveness part that we like, that we don't need to affect the PLC, we can also parallelize. So if you have an emulated instance, we can run as many as we want. We can get an Amazon cluster and then run 1 million of them at the same time. So it helps us accelerate fuzzing, and fuzzing typically involves sessions that can be millions of possible inputs. So the ability to scale up easily is very important in this context. I briefly mentioned the emulation types, whether you do a binary directly, when you do partial system, or you do a full system emulation. Every abstraction is different, gives you different abilities and also different performance. All right, on the emulation side, I'll quickly go through this and finish that part. IFSET is a platform we created. It's available on GitHub. We published a date paper with that. And what this does, it still needs, so for emulation to be accurate, we need to have the exact kernel version, and we also need to have the configuration files and other things that are needed for us to build the right kernel, so it can be accurate and we can see the vulnerabilities of that instance. So modern PLCs allow you to connect to them somehow remotely. That's one of the newer capabilities. WAGO itself supports both FTP and SSH. You just need to employ one of the two ways to connect to the PLC and extract a couple of files, right? So the files we need to extract are the kernel configuration, as I mentioned before, and the file system, right? Because the file system will have everything we need to load the QEMU and then get the emulated instance. So after we get that, we build our image with the file system and the kernel configuration. We mount the image so we can process it and add, because we need to modify the initialization scripts and we need to add the fuzzer. So in a way, our fuzzer will be inside that file system, right? So I extract it from WAGO and I put my fuzzer there. I could have put the fuzzer in the WAGO too and then extract, right? But it doesn't make a big difference. And then I add my fuzzer because the fuzzer is internal to the image. So I use that to start my fuzzing sessions. And then I can boot that. We have demos and stuff. I'll be very happy to send you demos of those setups, but we'll have it on GitHub, so you can feel free to download and use it directly. Typically, those devices have default credentials, so you can log in and start fuzzing directly the emulated instance of the PLC. The problem with fuzzing in that context is that the firmware, it's a big blob, right? This Codesys runtime, it's a big binary. In a way, it's a virtual machine because it runs external code. And it's also kind of built with anti-debugging properties. Probably Codesys wanted to ensure that it won't be reverse engineered and sold by others. So that, if you have to analyze that, it has massive size and complexity, right? It's extremely difficult to reverse engineer directly the runtime. So we're looking mostly for shorter wins. And besides the firmware itself, there are a lot of dynamically loaded functions, depending on what is the setup you have for your PLC. Let's ask him, what if the PLC does not support connection? Knowing that you have to have a way to get the firmware out. So worst case scenario, if no remote connectivity exists, typically that firmware exists in an SD card. So you need to physically take the SD card out, but that means the PLC should be offline for you to do that. It's very common that if you have a PLC that's Linux based, this was done so you can have all these nice capabilities of connecting through SSH and FTP. So I cannot think of a case that there's a Linux operating system but no SSH or FTP, unless it has been, on purpose. Those have been blocked. So to retrieve the firmware, you have to be physically next to the PLC and get the SD card, or connect. Actually, it has an Ethernet cable, so you can plug in a cable to it and get information from the PLC directly. But I mean, it really depends on the PLC, right? I would never expect the PLC to have an advanced Linux kernel and not have those capabilities, because that's a marketing pitch of these companies, that we give you all these advanced features for the PLC. But in a way, you have to find somehow the framework so you can have an accurate instance to fuzz, accurate emulated instance to fuzz. So I mentioned the anti-debugging. The presence of so many threads is creating a problem in our fuzzing sessions because they have their own life. So it's hard to manage also and to synchronize them, to manage different inputs and different threads. So that's another challenge we need to address when we talk about fuzzing the runtime. So I don't want to go into detail, so we can go to section to class 6 and talk about Stuxnet. I mentioned for the fuzzing part, I posted the paper we had on Usenix earlier this year. So you can read the paper, we have the code, the video is there, the presentation is there. So you can see exactly what we did to enable fuzzing for Codesys. So I'll skip these and I'll go to, so this is our setup, right? So that's our WAGO PLC. And this is our fuzzer. We just use AFL, right? We didn't do much magic on the fuzzing side. That our magic was the instrumentation, the ability to have visibility to the fuzzing sessions, and the way we're controlling the inputs, because that's not easy. And we did that by controlling the thread that does the input-out management, the K-bus. So that's what enabled us to have proper fuzzing in that setup. We have some results. We found some bugs, some crashes. We reported to Codesys as well. Not that many, though. But I mean, it was a start, right? I mean, it was a way that we started looking at these things. And the last thing I'll say on this part, again, the reverse engineering, the last thing I mentioned was using paper. You can see the video, we have it posted on GitHub. The emulation part was the date paper we had last year, and the reverse engineering part of the binaries was NDSS paper we had 2 years ago. And we had a presentation similar to this. How can you use emulation and fuzzing for finding 0 days? That were presented to Black Hat in a few months back, and I have also uploaded in our channel the presentation. So all these resources will give you much more detail about what I presented to you today. And feel free anytime to email me if you have any questions or you want to discuss more about these things. All right, so let me finish that and go to dissecting Stuxnet. So that should be the screen. Any questions? Thank you for asking questions, Leonida and Solon. I really appreciate it. All right. So by popular vote, you wanted to get some more information about Stuxnet. So that's what I'll present now. Is my screen visible? Just checking because that's through the web.
Yes.
Yes.
Okay. Thank you. Thank you, Steve. Stuxnet, right? That was the first answer given when I asked what kind of industrial control system attacks you know. And that's the most famous one. There are movies, there are books about it. And what I'll try to do here in the next hour is that I'm going to give you more technical details about what Stuxnet really was, right? Because we know a lot about what it did, but it's unless you really dive into the code of Stuxnet, you won't really understand how it did it. And Stuxnet is very interesting because it still is the only malware we know that included PLC code in its payload. And that's very unique about Stuxnet, right? All the others are typically malware for Windows or Linux or other computers. But Stuxnet was very unique that it included Siemens PLC code in order to do some things that we'll see near the end of this presentation. Why are we dissecting Stuxnet? Well, you know, if you at some point decide that you want to become the good guys, blue team, and you want to protect an industrial control system against attacks, Stuxnet has a lot of technical lessons, right? Stuxnet would contain many things, many different payloads. So dissecting it into these components will give you an idea about what do you need to, what kind of security controls you need to have in place that are needed in this context. And again, I'll repeat it, security is not something you can do 100%. You're adding security controls, and every control is reducing your risk. But you need to know what to add, how to add it, monitor it, and so on and so forth. But Stuxnet itself has a lot of lessons to be learned. Stuxnet, in also my mind, is an excellent example of no matter what you do, if an attacker is very motivated, they'll find a way through, right? That's something you should keep in mind. And because of that, and having that mindset, you should come to, again, a second step that, what do I do after my attacker is through, right? Never say, I'll just prevent all attacks. That's a terrible security posture. You always say, I'll reduce the attack surface. I'll try to prevent all the attacks I can. And then I have a plan and a budget for post-attack, because I'm definitely getting attacked and the attackers will get through. So Stuxnet complexity really tells us the story of, it doesn't matter how many things you do, the motivated attacker will get through. Because in a way, that attacker here had unlimited budget. Once you have unlimited budget, at some point, you'll find a way through, right? It's all about how much money you can spend on the attacks, how much money you spend on the defenses. It creates a balance. All right, it's heavy on the technical content, but you asked for it, so it's not my fault. But I would apologize to non-technical experts, because it revisits many things from application security, network security, and computer security classes. And while I would hope that you have taken some of these, if you haven't, don't worry. The idea is more to get a sense of what Stuxnet actually did. All right. So Stuxnet was uncovered in 2010. It was working for a few years. There is suspicion that there was another version before it. Stuxnet probably is the malware that there are allegations, but we all believe them now, right? It's common knowledge about who did what, while for other cyber attacks, we're still talking about suspicion or, again, allegations. So, but Stuxnet appeared everywhere in the world, but what it affected mainly was a uranium enrichment plant in Iran, in Natanz. And the way it affected the plant is that you see on the right side, there's some gas centrifuges, and those are spinning in some frequency. The frequency that they spin is being controlled by a PLC. Remember, a PLC interfaces with the real world, right? So it was actuating the centrifuge. So the centrifuge was the actuator of the PLC. So it was getting the commands from the PLC. So the exact frequency of actuation was given by the PLC. And that was a Siemens S7 schematic one. So you can imagine if someone can take over the PLC and send different frequencies that the centrifuge should be operating at, this can have different effects. One would be you're not producing the right product. So if you spin at a different frequency, your process is incorrect, right? Because it was built to, centrifuge had to spin in a specific frequency for the proper process to exist and the material to come out as it was supposed to. So there's a quality degradation, right? That's one effect. Another effect would be leading to conditions that are unsafe for the centrifuges themselves, like spinning them outside operating conditions, so you can damage them and they have to be replaced. Stuxnet never led to, like a catastrophic event that something exploded in the factory. The only thing Stuxnet mainly did is spinning the centrifuges in an abnormal way, causing them to degrade faster. So it was discovered because someone said, why are the centrifuges breaking so fast? That doesn't make sense, right? And they started investigating, and then they found the malware. So, but the malware, again, it was at the end, it ended up with the PLC control. Even though it had many steps before, it ended up at the PLC that connected the centrifuges, and then it would spin them in abnormal ways, and then they would degrade and break, and they had to be replaced. So that's pretty much Stuxnet, right? But the fact that, you know, someone from afar, from the other side of the world, was able to create physical damage to your plant was something extremely unique at the time. And it was the first incident of cyber warfare that was publicized. So if you look at exactly what Stuxnet was, even though it was everywhere as a virus, it only operated under very specific conditions. Only if it found a very specific configuration, it would actually deliver the payload. And this is because the authors of Stuxnet only wanted to affect a specific plant in Iran. Other plants were affected because they had similar configurations, but Stuxnet was found in so many more places than what it created damage to. So the Stuxnet checks, for example, is the resilient PLC? That's the first check. Does it spin between 800 hertz and 1200 hertz? That's a second check. This is a weird check because motors do not really operate in that frequency. That frequency typically appears with gas centrifuges, right? So those checks really are giving out what really Stuxnet was about. It was about gas centrifuges. And the physical layout it was after, it was exactly Natan's plant physical layout. So it's not hard to draw the conclusion that Stuxnet was targeting that plan specifically. All right, to summarize in a slide what Stuxnet did, right? Think that you have a plant, right? You can think of a plant, think of a plant, it has centrifuges, the centrifuges are connected to PLCs. The PLCs are controlled by an HMI, a human-machine interface. And the HMI will connect, it's typically air-gapped from the IT network. And then you have the IT network that, you know, it's the emails of the officials, it's the call center for people to call. So it has the IT part of the business. And the air gap means there's no network connection between the operations and the information technology. So there was air gap actually between where the centrifuges were located and where the attack started. So the attack started, Stuxnet would propagate in many ways. It had at least 4 ways to propagate. It would propagate both through USBs and through the network with different vulnerabilities exploited. Another extremely unique thing about Stuxnet is it would update itself using a peer-to-peer mechanism. So it had a command and control center it was talking to, but it would also talk to other Stuxnet instances in other computers in the same network. So it would create a chain that would eventually, you know, if you infected like 10 nodes far from the computer that the PLC is connected to, the HMI, then Stuxnet will still form a chain and would update itself throughout the chain, and then it would manage to have always the latest version attacking the centrifuges. These are all amazing features at the time. I mentioned the command and control center that will receive information from. So the command and control center, it serves as getting new versions of Stuxnet, but you need internet access. And the operations environment will never have internet access. It's one of the security mechanisms you first employ. No internet in a plant. So they relied on someone walking in with a USB, for example, or with an infected laptop for Stuxnet to propagate in that local network of the operations. Stuxnet was also hiding itself through Windows rootkits. It was looking for antiviruses too. So if it found specific antivirus versions, it would behave differently. And that's on the loading process, the way it was loading itself, depending on what antivirus was installed, because different antiviruses would capture the virus in a different way. And as I mentioned in the previous slide, it would fingerprint the system, and only if it found an extremely specific configuration, it would deliver a payload and sabotage the system. And the last thing that made it extremely unique is that the PLC code of the Siemens PLC would have been modified. That's the extremely unique part. Everything else I discussed so far, command and control, peer-to-peer updates, rootkits, this is all IT stuff, right? But the end, the HMI to PLC connection, Stuxnet took over the Siemens update and the Siemens database, and then that was, it would move new code to the PLC, and that code would create the final payload of spinning the centrifuges in a very abnormal way. So spreading, this is what I tried to describe before. You know, it has to somehow come in to the local network, right? So air gap is typically broken by USB sticks, and you may have heard of the experiments. They in the US they threw USB sticks in the parking lot, and they see how many called home, and many of them did, right? Someone would just find a USB stick on the ground and would pick it up and would put in their computer. So infected USBs, infected laptops, bringing your own laptop in the factory was also a way for propagation. So at some point, somehow it could be bribing, right? We don't know exactly how it started. It could be someone paying one of the employees to put the USB in one of the computers. But it made it past the air gap easily. So once it's within the air gap environment, right, everything is connected to everything. So it started propagating from computer to computer in different ways, either using a Samba vulnerability that's very notorious. It affected many computers for many years. Using a printer vulnerability, in a way, a printer, the spooler, not a spoofer, the spooler would, if you send a special file, it will execute it after printing, right? So it was using that vulnerability to execute through printers. Network shares, it would write itself in shared drives, or it would infect step 7 projects. So when you load it in another computer, that computer will infect it with Stuxnet too. The point of all these propagation methods was to eventually reach the HMI that is connected to the PLC. Once it arrived here, that was game over, right? It had access to the PLC, and then it knew exactly what to do at this point, and this is affecting the centrifuges. Timeline, no need to go over it, but in a way, we found the vulnerabilities used by Stuxnet were discovered some years before Stuxnet itself was discovered. And then around 2010 is where we found out what's happening with Stuxnet itself. If you look at infection statistics of Stuxnet, in September 29, 2010, there were over 100,000 infected hosts, right? So as I said in the beginning of this talk, Stuxnet went everywhere because its purpose was to massively propagate everywhere it could, but it wouldn't do something unless the configuration was appropriate. So there's a very high chance that many of us had Stuxnet in our computers and we didn't know about it because it wouldn't do anything, right? It would just wait to propagate further to some other computer. But if you see the statistics of the infected hosts, it's very clear what the target was, right? Most of them were in Iran, and 60% of the hosts were in Iran. And the way we found that number, Symantec found that number, is by monitoring the request to the command and control servers that Stuxnet used. So when they found the malware, they reverse engineered it and they saw the command and control URLs, and then they started monitoring traffic to that to understand how many hosts actually have Stuxnet, are affected with Stuxnet. Further breaking down the previous graph, so if you take only the hosts that have Siemens software installed, then Iran is also first here, right? 67% of the hosts were from Iran that had Siemens software installed and infected with Stuxnet. So infection per country, so you see what was happening, right? So Symantec started monitoring on 20th of July, and you see the new IPs, the new IP infection per country, and then there was a sudden drop in August 22nd, right? What do you think happened on August 22nd? So Iran is not reporting any new IPs, right? So that doesn't mean Stuxnet was eliminated. That meant that Iran blocked access to the internet for the country because they realized what was happening, and they realized that many of the hosts were talking to remote servers for command and control. They fully blocked the internet of the country in order to start mitigating the attack, to finding the host and cleaning them from Stuxnet, right? That's why we see this huge drop in the on August 22nd. Stuxnet came in different waves. This is not very interesting. So there are 3 times that Stuxnet was injected in different ways, remotely or locally. And that created different clusters of infection. The way Stuxnet propagated depending on the initial infection, and then Stuxnet would also delete itself after a number of propagations. So if it propagated more than 4, I think 3 or 4, then it would just delete itself, so that it won't cause a massive problem and try to mostly laterally move through the network. This is focusing on domain E attack. That was the final one and the biggest one, the one that actually reached the centrifuges. There's more information in a Symantec report that we have to share with you if that domain interests you. All right, let's see a bit about the architecture of Stuxnet. Stuxnet was a DLL. Heike is asking a question. Looks like all countries act in a similar way. True. There was at some point there was, if you see that the drop, only probably this time this is where I think the command and control centers themselves were blocked. But I'm not sure that's the countries that the countries responding, right? India, Pakistan, Russia. So again, remember these statistics are just what Symantec was observing as traffic to the command and control centers. And Iran blocked all traffic. Maybe this happened here. They blocked access to the command and control center specifically, or the ones controlling that, like GoDaddy, like they brought them down. So Stuxnet is it's just DLL. It mainly consists of a dynamic library file that has exports and resources, right? If you have done Windows programming, then DLL is a collection of functions and resources. It's not executable because it does have a main function, but it has functions, right? That's an export of a DLL. And resources are data, is things that is not code and can be dropped by the DLL. So it also had some configuration blocks. We'll see why they were important. So this dropper had all components in a section named stub, and this is how this name Stuxnet came from. This stub thing that had all the functions to be exported, right? And if you read the functions on the right side, they're functions that operate Stuxnet, like infect USB drives. Hook to the API of step 7, remove yourself, verify installation, verify version, initial entry point, uninstall of Stuxnet, infection of removed drives again, net propagation, command and control, and so on and so forth. So this is all the functions needed for Stuxnet to be self-sufficient, right? It can do anything: infection, installation, updates, removal, and so on and so forth. All right, so a DLL, it's being loaded somehow, right? And many of the antiviruses of the time, and now too, in order to ensure that there's no malware in those files, DLLs are executable, they're looking for behavior. Right? And behavior blocking was a way antiviruses would have detected Stuxnet, but Stuxnet knew antiviruses would have been there, right? So in a way, what Stuxnet did, that was a very smart thing, right? So instead of calling the library, load library, because typically rootkits, malware are calling library functions, right? Operating system library functions. So what the Stuxnet would do, it would call it with a wrong file name, and no library would not execute. So antivirus would stop checking about what happened. But what Stuxnet did is that it had the rootkit on one of the DLLs to check for those special names. So when it was loading itself, when it was doing its job, that a rootkit installed before would take over those special crafted file names, and then it would execute them separately. And it was some specific patterns. Now we're going into too many technical details, but these are the functions that this NTDLL was hooking in order to override, to bypass behavior blocking when when Stuxnet was doing some of the functions. Stuxnet was injected in various ways depending on the antivirus installed. So what it would do, it would take over an executable, and depending on the antivirus involved, it would be a different executable, right? So if it was a Kaspersky antivirus up to version 7, that was the process, LSASS. 8 to 9 would actually hijack the antivirus itself. McAfee would be WinLogon, and then LSASS would also appear in most of the other antivirus too. Remember, when malware is loaded, how it's loaded, you exploit the vulnerability to execute your code, and that code is taking over the process now. So that takeover of the process is what executes the malware, right? And then you delete the process or you create a new one and you leave the previous one alone. So the question is, what process is being overtaken? That's really up to the vulnerability that Stuxnet used, and also what is the antivirus installed. So I mentioned that, so injects the DLL into existing process. It looks at what's happening, it extracts a template, portable executable, and then Stuxnet will have a configuration block. So Stuxnet would know exactly what the computer was, what's the computer operating system, and what's the computer IP, and some other flags that we'll see later. So that's needed because for different computers, Stuxnet would have different payloads. So depending on the version of Windows, it will use another payload, another vulnerability compared to other versions of Windows. So it would hijack things in a different way. And this is amazing. Once you realize how flexible Stuxnet was, you start understanding how much work went behind that malware. So again, it was a mostly Windows-based malware. Most of the HMIs run on Windows. HMI is the computer that interfaces with the PLC. And it's a regular computer, right? It's not hardened or anything. So when you have a Siemens PLC, Siemens will give you software that you run on a computer, that's the HMI, that interfaces with the Siemens PLC. And you can send commands, monitor, and so on and so forth. So this is a sample control flow for export 15. Remember, export 15 is mostly taking over the process. It's not injecting Stuxnet yet. It's trying to figure out how to, what process to take over. So let's take a look, right? So remember, export 15 is one of the functions of Stuxnet. So it would take, first step to check configuration. Second step, it was checking whether you have 64-bit or 32-bit, right? The authors of the malware knew that the computers of interest were all 32-bit computers. So one check they would do is to check if the computer is 64-bit, and then they would not inject Stuxnet. Then the operating system would have been checked whether it's Windows and one of the supported versions. Stuxnet would infect XP, 2000, Vista, and Windows 7 computers. They had payload for these operating systems. And then it checked whether the hijack process, and we'll see what hijacks mean later on, it has administration rights or not. If it doesn't, it takes administration rights. If it already has administration rights, it can do whatever it wants, right? It's an admin process, so it's easy to do whatever you want. So if you have admin rights, you check the antivirus, as we discussed before, remember? You choose the process based on the antivirus, you create your executable, and then you inject it in that process we just discussed. If you don't have administration rights, then depending on the operating systems, you use one of the two exploits built in Stuxnet. One would be this keyboard thing that was problematic with XP 2000, the way keyboard layouts were loaded, or a task scheduler problem that was not checking for the end of the tasks. So you could exploit that in order to run your own code that ends up executing your payload. So one of those two, because changing keyboard layouts is an admin process, then you would restart being admin. And this task scheduler is also an admin process, right? So if you take that over, you also start as an admin process, and then you can do the same thing you were doing before. So this payload here, the Win32K, what it was, so you get an idea of what we mean about payloads, right? And content is, it was a local privilege escalation. What it did is, there was this system file from Windows that was eventually patched in 2010 that was responsible for changing the keyboard layout, right? You could load, if I'm Greek, so I have English and Greek as languages in my computer when I type. And this keyboard layout is actually loaded by user programs, right? I do it, and I do it through the operating system, but still, the keyboard layout has to go through the operating system. So what this vulnerability was about, it was an out-of-bounds check. So you would say, give me keyboard layout 5. And then it would go to this location 5 and get the layout 5. But if there was no bounds check. So if you say, give me layout 300, then it would just go there and execute stuff there, right? So most vulnerabilities are lack of bounds check. So same thing here. So it was 0 day, means it was not known at the time when it was being exploited, but through that, the giving a big integer would lead to indexing something else, and then through that you just put the right number and you execute whatever function you want, right? So what the Stuxnet would do is would find that array, find memory you can execute, and then inject the code there, and the bad indexing would lead to call to this modified function. Again, this is a bit more technical, right? But it is an idea. Now we're still on how Stuxnet will start its process. If it needs to start, it needs to inject itself. To inject itself, it needs to find and exploit a vulnerability. So it had a lot of vulnerabilities it could exploit. That's an example of it. This 0 day vulnerability in that Win32 file. Then, because when you call the keyboard layout change, this is an administrator process, right? It's a root process, kernel process. So since you're asking for the layout, Windows will do that for you. So you would run this bad code with kernel privileges, and then you're done. You have privileges now. All right. So that's on the executing with admin side, right? So we use the previous DLL export in order to find, in order to be able to execute our own code. But the question is, what do we do? What kind of code? Right now, you have to infect the computer. You have to install Stuxnet. It has to be present. Right? To do that, again, there's a process. It checks the configuration file. it had a specific magic value it was checking. So that was like a safety switch. So if a specific registry address had this key, then Stuxnet would abort. So the way to stop Stuxnet in your computer is to just add this registry value, right? Because Stuxnet used that as a mechanism to ensure, of course, that it won't affect computers of the people involved in the attack or others that are allies of the perpetrators. And if you look, I mean, that looks like a date, right? That's 1979, May 9th. And it is a significant day. I don't remember the exact details for Israel. That's one of the things, people used to attribute the attack to Israel and the US, right? And in a way, it has been accepted that the attack originated from the US and Israel against Iran and against the nuclear program of Iran. So if the key was missing, then Stuxnet would check for a date. We'll also see whether it was past the date, so it had an expiry date. On every code, actually, it was an expiry date. And then check for XP or Vista, created some utexes, configuration files. Remember, this is admin privileges, so it can do whatever it wants. And then it just loads the actual Stuxnet payload. Export 6 will give the right version. And if Stuxnet already exists in the process, it would override with a new version, or it would do it would keep the version it has if it was newer. Another thing that's unique about Stuxnet, because it wanted to be there on every restart. If you restart, right, the Stuxnet will go away. So it needed to have persistence. And to achieve that, what you need to do is to inject it in a location that's loaded automatically with the operating system. And that's typically the drivers. So drivers are prime targets for attacking because they're loaded with Windows. So if you inject Stuxnet in a driver, then you're done. But to override a driver, you need a certificate, right? I mean, you have to have a valid driver because Windows is checking for the certificate of the driver and whether it's signed properly or not. Otherwise, it wouldn't install. Well, Stuxnet authors stole certificates from companies in Taiwan, and they used those certificates to inject Stuxnet in the drivers so they can have persistence and the ability to boot Stuxnet with the computer. These are the two files here, right? The sys files contain Stuxnet rootkit. And then it would do things that hide itself, because once you're admin, right, you do whatever you want. It would create a rootkit service that if you're looking for files in a directory, if Stuxnet files were there, then the Explorer would skip those files. It wouldn't present it to the user. So you wouldn't see if something is there, either files from Stuxnet. And then we'll try to propagate further, either in a removable drive. So you have a USB drive inserted, then Stuxnet will infect it. It was a step 7 software project there that will also be infected too with different exports, right? Export 32 would infect USB drives. Export 2 would infect step 7 project files. And then it would exit. So after that, Stuxnet has persistence and also tries to propagate further. Any questions on the architecture of Stuxnet? All right. Moving on to the loading part. I did mention that already because it had to be loaded with the boot. It had to drop a driver file. That was this mrxcls.sys. That was export 16. That was properly signed because someone stole the certificate, so they could sign their own drivers from Realtek certificate. I mentioned that it's executed every time it boots, and lots of technical stuff, like it goes for after specific processes. Command and control, that's also very important, right? Because, you know, when you first infect, you have limited understanding, you don't have full understanding of the topology of the target system. So malware very commonly have these command and control servers that they send information back to the attackers, so the attackers can analyze the information and make decisions or send new versions of malware. And the way Stuxnet did that was through two command and control servers that we know. And that is those two, mypremierfootball.com and todaysfootball.com. These were done with HTTP connection on port 80. This is, these servers were located in Malaysia and Denmark. And this is what Symantec was monitoring to understand how many infections per day existed. Can someone tell me why was HTTP and port 80 chosen for this command and control operation? I just was getting tired. So, you know, if you think about a system, right, a corporate network, so you typically block, if you do have a proper firewall, you block most traffic, except traffic that you think is legitimate, right? So traffic, HTTP traffic on port 80, that's regular internet browsing. So in a way, if you block that, nobody can access the internet, right? So if you use other ports or other protocols, Stuxnet wouldn't be able to communicate because there's a very high chance someone would be looking at these at other ports or other traffic. That's one thing. And second thing is Stuxnet sent the information back to the control center as ASCII code. So it wouldn't use weird binary representations. So in a way, it was sending a long string back to the command and control center. And you can see here what it was sending. It was sending the operating system versions, some configuration data, the computer name, the domain name, and IP addresses of interfaces the computer had. And if it was a step 7 computer, it would also send a specific string from configuration data. So it could just, in a way, it was doing reconnaissance. It was extracting information from the computers, and then the authors of Stuxnet would see that information and update Stuxnet. And then we had a new version of Stuxnet that would go even further because they knew the exact versions that were used in the computers currently infected with Stuxnet. So it would send a few stuff back, as you see in the slide, and then it would kind of encode it, and it's not encryption, right? It would just XOR it with FF, so it won't be clear data. And then it will be sent back to the command and control centers. So export 29 was sending back. It happened in 2 steps. First, check whether you can access the internet by going to msn.com. And if you can, that means you have internet access. Then you build the network packet, you XOR it with that string here, and then you send it by accessing the internet again, right? You do mypremierfootball.com index, and you send the data through this URL string. And as I said before, HTTP and ASCII parameters is a very common way to bypass firewall blocking rules. On the receive side, it would come back in the HTTP content section. Similar way, different XOR key. You would get back something. It could have a file or not. If it had a file, then you would download it. So this, I can send you any file to execute, enables Stuxnet to have backdoor capability, right? You could, in a way, you can execute anything you wanted on the other machine. And once you have that option, the capability, you're done, right? I mean, you just move forward after that. I did mention the rootkit side. Stuxnet has the ability to hide copies of its files. So if you were to browse, your drives, then it would skip the Stuxnet files, and that happened by that driver we discussed before. So anytime you would inject, so this device driver was also responsible for intercepting traffic going to the to the movable drives. So when traffic was going back and forth, Stuxnet would intercept it and act accordingly. So here you see, actually, these are the files typically used by Stuxnet for infection. So a Stuxnet infected file, a Stuxnet infected drive, sorry, it would have those files, right? Copy of shortcut 2, copy of shortcut, and all these things, and 2 temp files that they have some numbers that pass a very primitive checksum, right? Their modulo 10 is 0. And these link files are shortcut files, and they're used to exploit vulnerability with loading the images of shortcuts. That was another vulnerability Stuxnet used for infection. So, you know, if you run a modern antivirus that, you know, knows what Stuxnet was, then it would find those files as malicious, right? Your copy of copy, your device driver are being mapped as Stuxnet files too. So what Stuxnet did through the rootkit was to hide the existence of these files in the USB. So if you had those files and you put your USB in your drive and you start Windows Explorer, you would see 0 files, like nothing would be there, because a rootkit would hide those files before being displayed to the user. All right, so that's the loading side. Let's go to propagation. I did mention already, it propagated through 2 ways, either network or removable drives. On the network side, it goes through peer-to-peer communication. So computer to computer, Stuxnet to Stuxnet, it would be one way. Another way would be WinCC machines. That's the database server of Siemens for project files. It would propagate through network shares, all these vulnerabilities, right? It would propagate through MS-10, the printer vulnerability, or the Windows Server service vulnerability. That was the propagation. Vulnerabilities were used for different purposes, right? Either to inject or to propagate. So here we're talking about the propagation side of Stuxnet. On the removable drive side, it uses 2 ways to propagate. One is that vulnerability I briefly mentioned before with the shortcut files. And it would also use autorun, right? For the ones that are older, remember the autorun.inf, and would just put a CD-ROM, a CD in the drive, and then autorun.inf would automatically execute. So here was a similar capability and a problem with the parsing of the file that Stuxnet exploited in order to propagate. Peer-to-peer communication, I mentioned it briefly. It talks from machine to machine through RPC. This is getting too technical, right? The WinCC part is when you know, you load project files in Siemens, but this WinCC project database server had a special hard-coded password for administrator access. And if you know that, you have access to it. So Stuxnet would say that malicious SQL code, and part of the query of the code would be Stuxnet itself. So Stuxnet would do an insert SQL query to inject Stuxnet as a database entry, and then it would export that database entry as a file. So now you have Stuxnet as a file in the other computer. And to execute it added also a modified view in order to execute the just downloaded binary. This is what I just said, right? It injects itself as an entry through SQL and then executes itself. And that's the way. Another way, this, you know, when that's an example of an HMI, right? An HMI is a view. It gives you a view of the process, right? And the process actually can have different views. You can have a view of mostly seeing what happened with the sensors, another view looking at the actuation. So a view is being loaded by the HMI. So Stuxnet would inject itself also in a view. So when that view was loaded, Stuxnet will be loaded too. So you can see how many ways Stuxnet had to propagate further, right? It's pretty amazing when you start looking at the malware itself. Other ways to propagate, we discussed network shares. When you have in Windows shared drives, anybody can access them in the network, right, in the local network. So Stuxnet will look for shared drives, and if it finds something, it will just copy itself. And then it will try to find a way to execute, and we'll see how. Another way to propagate was a printer vulnerability, and the fact that shared printers execute code, which is a weird thing to do. Another problem, another constant issue with constant source of vulnerabilities are printers. The way printers are being shared creates security problems. So here, what Stuxnet did is would send a file to be printed, but when you send the file to be printed, you can put it in anywhere in the file system. You can tell it where to put it, right? If you impersonate the spooler certs. So you can, when you print, you can print to a file, and that file can be Stuxnet. So in a way, it remotely printed Stuxnet in that local printer in a file, and then it printed it in a location that is checked in intervals and automatically executes whatever binary shows up there. So if you can inject a file, so what it did, it created a file in another computer, but the file was specially placed in a location that there is a daemon that routinely checks for files, and if it finds something, it will execute it. So that's how it executes Stuxnet on the other computer. That's a vulnerability that has been fixed since 2010. And Stuxnet had an expiration date too, by itself. Another vulnerability was buffer overflow one. That was an older one from 2008. But remember, those PLCs and those systems are not updated. So if vulnerability exists 2-3 years now, there's a very high chance it's still applicable to the system because those systems are not updated regularly. And that's a good example, right? In 2010, they were still using vulnerabilities fixed in 2008. But unless you apply the patch, the vulnerability remains and it's still there. So that vulnerability 2008 one was a buffer overflow. That's the Samba one I mentioned. Samba version 1 is outdated and deprecated. Actually, it has to be disabled in every system because it has problems. So Samba was used for file transfer over the network. So if you send a bad string, when you copy, you have buffer overflow, you overwrite the return address, you send your own code, you execute whatever you want in a remote computer, right? That's a very vanilla buffer overflow problem. Stuxnet still checks 4 things. It checks whether it is before 2030, that's an expiration date much further. But it does check for what antivirus are looking after, right? Because antiviruses would look for malware that would exploit this vulnerability. So Stuxnet would check for antivirus versions before using that. So it would have many weapons, right? It would use the right one at the right time. So now we talked about the network vulnerability methods. Let's talk very shortly about the USB ones, the removable drive ones. The link one I mentioned is a problem of Windows that when you get the thumbnail of a shortcut, it will try to find an image file in the file, and it will do it in a very wrong way. So to do that, if you look, so something like this, right? That's a shortcut to a file. And that shortcut typically will try to pick up an icon from the file, right? So it kind of redirects the execution of the code to somewhere else, to another file. And that's how the vulnerability would be created. So in a way, what this did is by simply viewing the folder, Stuxnet was able to execute code. How this happens? Well, what they just said is when Explorer would open that file, it loads the DLL that's specified in the file to display the icon. But remember, a DLL has also code. So if it doesn't go to the right place or the right location, you can execute any code you want. If you don't check what you're doing, right? If you don't check that you're in a resource and you're actually in code, then in a way you can execute any code you want by just opening the contents of the USB drive. So that's the vulnerability fixed in 2010. So in this way, what Stuxnet would do would execute this file, the 4141, that would load 4132, but it would also act as a rootkit and hide the existence of those two files we mentioned before, right? So we had the LNK files, remember, that had this exploit we just discussed, and the TMP files had actually Stuxnet in them. One is the loader of the other, right? And that's how it did it. No need to go over too much detail about this. The autorun.inf side, that was a much simpler exploit. Autorun ignores everything after a point. So Stuxnet used that to add Stuxnet in the autorun.inf file. So autorun.inf will just execute Stuxnet when it was first run, right? So easy to do, easy to exploit vulnerability. All right, very quickly as we're nearing the end, what I think the most interesting part, everything we talked till now was how Stuxnet was moving throughout the IT network and Windows machines and printers in order to arrive to the HMI, in order to arrive to the computer that talks to the PLC, right? So that's it, that's all we saw so far, loading, injection, propagation. So now we spend like 5-10 minutes to see what's happened with the PLC itself. With the PLC itself, Stuxnet would change the PLC code. And to do that, it would go after the functions of the PLC DLLs. And there was a specific one, where is it? A specific DLL being infected, right? And if you see here, I have an example of this ladder logic for step 7, and it has some code, right? Stuxnet would add to that code its special code that does other things. It does it in different ways. No need to discuss all these things, but the only thing you need to remember is it essentially hijacked the DLL communication. The PLC to the computer were talking through a specific DLL, right? This S7 OTBXDX. So that's all the PLC block exchange between the HMI, the control computer, and the PLC. So Stuxnet would overwrite that file, and that it is the infected file that it either redirects to the proper file or it does something more, right? And only a few functions were overloaded, and I don't have them here, right? But this is the Stuxnet code in step 7. So it would add extra blocks. So this code you see here, this is extra code added by Stuxnet, and it does something that we'll see in a few minutes. So that's it. That's what I was discussing. So step 7 would send a message to the PLC. The malicious DLL will read it, and then it will send it to the PLC or read from the PLC. If something was malicious, the DLL would also hide it from step 7. So it would also hiding things back and forth. So it was intercepting, it's like a rootkit, right? It was intercepting communication, hiding what was really happening underneath. The infection process, this part is the interesting part because this is where Stuxnet was checking about the exact configuration of the centrifuges, how many of them are connected to how many modules, communication modules, And only if it found a specific number of centrifuges connected to a specific type of communication modules, it would execute the attack. This is where we can easily understand it was extremely targeted attack. So it would check that offset to be equal to this special value. That means it was this communication module, 342. And then it would see whether these values add up to more than 33. Because the Natanz plant had more than 33 centrifuges connected on the same communication module. And those two special values correspond to manufacturers, one from Tehran and the other one from Finland. Yes, Finland. And because through reconnaissance, the attackers knew these were the two types of centrifuges used in that specific plant. So now, after it found the configuration it needed, then it would send a different payload for different centrifuges, because a centrifuge manufactured by another company has different physical properties, and it's difficult. It needs different abnormal spinning in order to be broken. So depending on the type of the centrifuge, it will send different payload as the abnormal spinning part. So it would do a lot of stuff, replacing the communication between the module. So there's a PLC and there's a communication module after the PLC that actually talks through Profibus with the rest of the system. It would add an extra block on this OB1, that's the beginning of execution. And this is how it would start. And the attack itself, so that's the PLC code. That's how things talk to each other, right? So these are PLC blocks, functional blocks. So some of them are fake, as you have this receive block. Let me point out. So you start from here. So you have some added stuff from Stuxnet that reads specific things, and if it finds a command or some kind of payload, it would send different packets. The way you communicate to the centrifuge, you send a packet and say, this is your frequency now, change to 2 Hertz. And then you send another packet through Profibus and say, now your frequency is 1,000 Hertz. And it will do that all the time, for example, right? Send those packets in order to change the frequency abruptly, or maybe inverse. It wasn't doing inverse though. It would keeping the orientation. It was only changing the speed. And then through some kind of a more specific sequence, like you have events, a number of events. It wouldn't do it every day. For Stuxnet to be stealthy, it would affect every few days, and the days were matching some additional events. So it was collecting events, and then after some events were in place, that would happen every 14 days, for example. Then it would wait 2 hours, do the attack, wait again, and then wait for 14 more days. So it was destroying every 2 weeks or something, so as to remain stealthy and ensure that it won't be detected, that it affects in a more controlled time. I'll skip the rest. No need to discuss the rest. I'll stop here so we can chat if you have any questions. If your questions about Stuxnet, for the people who wanted to learn more about Stuxnet, then voted for that. Let me know if you have other questions that I haven't answered, or you'd like to meet to discuss something in the remaining 7 minutes. Yes, Solon. Solon, also, if you can, please unmute and talk so another voice can be heard, if that's okay with you.
Can you hear me?
Yes.
Okay, thank you for the presentation. My first question is this. PLCs and other ICS hardware have been built with air-gapped environments in mind. And this is shown from outdated security solutions like security through obscurity or no security at all, on PLCs and similar hardware. Since they didn't have to address security in a meaningful way, they made these machines have less computational power than really required for obvious cost savings. Shouldn't manufacturers start making more powerful hardware? And if this is not possible, is hardware-enabled or hardware-based security the solution?
So, you know, the inclusion of lower spec hardware, it's not really on the cost saving side because those PLCs are already extremely expensive. It is more related to the maturity of the process and the ability to be very confident about the robustness of the PLC, right? PLCs do very simple things. And if, you know, high performance processors like an Intel processor, like 2 gigahertz, they have caches, they have branch predictors, they have all these things that add uncertainty to the execution. So they're avoided in the context of PLCs. So one thing, high performance processors are not desired. Anything that adds uncertainty and non-determinism is avoided in the PLC world. So we're looking at embedded processors typically, and we like the ones that, you know, don't have caches, they don't add all this non-determinism. And older processors were built in older manufacturing nodes, like what I mentioned, 180 nanometers typically. And those nodes were both more mature, so you know the CPUs will not be susceptible to so many errors if you have high voltages, if you have abnormal temperatures, that they're a bit more robust, a bit more hardened because the transistors are bigger, so they're less susceptible to errors. So there are a lot of things to take into account when we think about what CPU to be included to a PLC. And since high performance CPUs are out of the questions, you don't have really many options after that. So I don't, however, there is a discussion. I've seen someone from Siemens told me that Siemens is creating PLC with machine learning, right? So companies will go after those things too, slowly, based on consumer demand, right? As machine learning is everywhere, we'll see more and more of this. But again, keep in mind that PLCs are there to stay for 20, 30, 40 years. So that transition will take time to happen, even if it starts.
So this machine learning module is going to be a hardware-based accelerator?
That's a good question. I don't have the answer to. I'll take a look and send you the article that mentions that. Let me make a note.
Okay, thank you very much. And for the second question, this is a much shorter one. Software companies are often criticized about vulnerable software, and bugs are reported in waves, which usually make headlines, and huge uproar follows against the code issuer. Firmware does not get the same publicity treatment in both vulnerabilities and updates that may be needed. Why do you think this is the case?
That's an excellent question. So think about the easiness of finding vulnerabilities in software and the easiness to find vulnerability in firmware, right? Firmware cannot be assessed easily without the device, without the hardware, because firmware is really running on the hardware directly, right? So it's very hard to find. That's why, for example, we did emulation here. In a way, we're taking the firmware because the runtime really hogs the hardware of the PLC, right? So firmware vulnerability analysis is a much more difficult problem. It's not a low-hanging fruit. You don't dump a fuzzer and run. You have to create, as in our work, we do through emulation, but you can do other ways, right? You can do symbolic execution of firmware or other things you want to do in order to do vulnerability assessment of firmware. So shorter answer, it doesn't scale. Vulnerability analysis of firmware is difficult and doesn't scale massively. That's why we don't see much of it. But firmwares have problems, and we see that with Intel firmware, right? All these vulnerabilities in Intel CPUs are in its firmware. It's memory management units, or it's other things it does. So they do exist, it's just not easy for many people to take a look at. That's why we don't see that many.
Fair enough. Thank you very much.
All right. Is there any other questions? Since this is last minute, feel free to send me an email. Very happy to respond. Very happy to discuss anything on the context. I do invite you, if you want to take a look, again, we have open sourced all this research, so feel free to take any of the tools and use them. And if you do, we'll be very happy to support you with that.
I have a question, Mihalis.
Yes, Maria.
Thank you very much, first of all, for the presentation and all the specific expertise that you have from the computer science perspective on these very timely problems. I have a question which I know that it may take a long time to answer, but maybe in the interest of time, maybe you can give us a short version. And it's, I would like to know from your perspective, what do you believe are some critical and important topics in this type of area for research? There's a lot of PhD students now listening to us, so it would be very nice for them to get your perspective on what do you believe it's interesting for the next, let's say, 5 years or so.
Maria, I wish you asked that like half an hour ago, so we can have the time to respond. And as you say, I'll try to give a short answer. It really depends on what level of expertise you're coming in. I can quickly give you some answers at the level that I know that Kios is working at, which is more on the control theoretic part. What could be a very interesting problem to look at is how can you run trusted code on a trusted platform, right? Because, for example, PLC has a supply chain, it has hardware fabricated in China, software developed all over the world. So you cannot fully trust the supply chain. You still have to use it, right? And control systems, from the control perspective, they have physical properties like inertia that could be extremely useful when we discuss untrusted platforms. So I think would be very interesting to see, and that people on the control side can contribute, is again the idea of trusted execution on a trusted platforms. It's a very difficult problem currently, and that could be one very interesting direction to go after. Another thing that comes to mind, but this is more on the CS side, is patching, and how can you dynamically patch? How can you ensure that the vulnerabilities cannot be exploited, even though you cannot patch? How can you create a structure in the PLC that prevents the vulnerability from being exploited by someone, right? Without patching or without doing something that, restarting the PLC. Other things I mentioned early, that, porting IT solutions, but in extremely lightweight, like lightweight machine learning or real-time sensitive machine learning and things like that, we haven't seen much work. Typically, we assume endless computation for machine learning models. And the PLC landscape is very unique, as I tried to motivate in the first part. So these quickly come to mind when, I'm trying to give a short answer about potential research topics.
Well, thank you, Mihalis. Actually, your third proposal, it touches a little bit on the comments by Solon before, and this idea of edge-based machine learning, which is very, very popular and in high demand. So do you see that maybe this type of solutions, edge-based AI, which by definition, it has to be very resource constrained, low power and so on, that this would be something that the industry would be willing to adopt
So, I mean, the issue with this industry is that it takes time to adopt anything. Things have to be rigorously tested. vetted in the field in a test bed environment, and they can, even adding encryption at the link layer and having a proper communication, that took like 15-20 years. So I don't see it. I think in the first 10-15 years it's going to be a hype, like we have machine learning for your PLC. But in reality, it will be much longer before it becomes something that industry will adopt and use in the product. Now it's more of a marketing trick. Siemens is doing it. I'm pretty sure others will follow suit. But that doesn't mean academics should wait for this to happen, right? I think with the right test cases, we may faster, like more quickly force the industry to move towards solutions that are, again, they can address unknown targets, right? That's the good thing about ML-based solutions, that they're after unknown solutions. Because currently we are signature-based with our antiviruses, some heuristics, but the fully unknown part that we see in ICS and we expect in ICS may be more properly addressed with machine learning.
Thank you, Mihalis.
So Mihalis, I think we are closing the day, your lecture, and too bad that you cannot teach every day for a week. There are many things that are exciting and are left open for curiosity and for learning more. So I really hope that the many PhD students are going to contact you, are getting excited about these. Working with industry in process control, I know how hot this is, and this is not going away. And there is a big issue about interoperability, as you know. And I mean, if you work with an S7 PLC of Siemens and you work with an Allen Bradley, you immediately see these things. And so there are also these aspects that are more on the social industrial way framework. So, but by now, by sure I will come to visit you, and as soon as I can. And in general, thank you so much for your very exciting lecture. And yes, this is closing the.
Thank you for the invitation, Thomas. It was an honor.
Yeah, well, honestly, Maria was kind of suggesting that, and I was so excited that it could be, yes. So it was actually, as usual in Kios, it was a teamwork, and
that's great.
Maria actually gave a very nice suggestion here.
Thank you.
Okay, so thanks everybody for attending, and don't forget that we have another interesting lecture in the afternoon by Professor Bruno Sinopoli, and so you see another side of the coin in a way. Thank you. Thanks everybody. Bye bye.